Hello, welcome to my presentation regarding how distributed SQL transforms cloud-scale data systems. The rapid expansion of global digital services has fundamentally challenged the limits of traditional database architectures. For decades, organizations rely on primarily centralized relational database management systems, RDBMS, that offer strong consistency but were architecturally optimized for vertical scaling rather than seamless horizontal distribution. In response, the NoSQL movement emerged, prioritizing horizontal scalability and flexible data models, often relaxing traditional relational constraints and strong consistency guarantees in favor of distributed performance. This tension has birthed a new category of technology, distributed SQL. This paradigm combines the familiar, rigorous transactional power of traditional relational databases with the cloud-native, elastic scalability of modern distributed systems. Distributed SQL is defined by its ability to spread data across a cluster of multiple nodes, often spanning different data centers or geographic regions, while appearing to the application as a single logical SQL database. Unlike traditional systems that require manual sharding, breaking the database into pieces that the developer must manage, a distributed SQL database handles data distribution, replication, and transaction coordination automatically. It preserves the ACID, atomicity, consistency, isolation, durability properties that are the gold standard for data integrity, ensuring that even in a global environment, every user sees a consistent and accurate state of the world. The architectural integrity of a distributed SQL system rests upon four core pillars: resilience, consistency, locality, and scale. These tenets allow the database to function not just as a storage engine, but as a robust foundation for global agentic applications. Resilience refers to the system's ability to tolerate component failures without data loss or prolonged service disruption. In a distributed environment, hardware failure is an expected event rather than a catastrophe. Distributed SQL utilizes consensus algorithms such as raft or paxels to replicate data across multiple nodes. If a node, a rack, or even an entire data center fails, the remaining nodes automatically elect a new leader and continue serving requests without manual intervention or data loss. This shifts the operational focus from traditional disaster recovery planning toward high availability and automated failover, though availability may still be impacted during major network partitions. Consistency is the non-negotiable requirement for transactional integrity. While many distributed systems settle for eventual consistency, where data may be temporarily out of sync across different locations, distributed SQL systems are typically designed to provide strong consistency by default, though some implementations allow configurable isolation levels for performance trade-offs. It provides serializable isolation, the highest level of safety, ensuring that even if two users in different hemispheres update the same record simultaneously, the database will process them in a way that prevents phantom reads or write skews. Locality addresses the physical reality of global speed and regulation. Data have gravity, and moving it across oceans introduces latency. Locality allows architects to pin specific rows of data to specific geographic regions. For example, a European user's profile can be stored on servers in Frankfurt to minimize latency and comply with regional data sovereignty regulations like GDPR. This geo-partitioning ensures that the database respects both the speed of light and the laws of the land. Scale in this context refers to horizontal elasticity. In traditional databases, scaling up involves buying a larger, more expensive server. In distributed SQL, one simply adds more commodity nodes to the cluster. The database automatically rebalances data to utilize the new resources, allowing the system to accommodate substantial traffic growth with minimal application changes, though careful schema design and workload distribution remain essential to avoid performance bottlenecks. The advantages of these tenets are best illustrated through real-world applications in industries where downtime or data errors are unacceptable. For example, in global financial services, a primary use case is the management of ledgers and payment processing. Consider a digital wallet used by millions. If the system is only eventually consistent, a user might spend the same $10 twice if they trigger transactions from different devices nearly simultaneously. Distributed SQL prevents this through its consistency tenet. Furthermore, the resilience tenet ensures that the Tier 0 payment infrastructure stays online even if a regional cloud provider suffers an outage, maintaining public trust and regulatory compliance. In the retail and e-commerce sector, massive seasonal spikes, such as Black Friday or Singles' Day, require extreme scale. A traditional database might buckle under the sudden surge of concurrent checkouts. A distributed SQL database allows the retailer to spin up extra nodes in the weeks leading up to the event and scale down afterward to save cost. Additionally, by using locality, the retailer can serve product catalogs from the nearest data center, reducing page load times and increasing conversion rates. Supply chain and logistics companies benefit from the locality and resilience of distributed SQL. Tracking an item as it moves through various global ports requires a system that is always available. If a local port's connection is severed, the distributed nature of the database ensures the data are replicated elsewhere, while the locality features ensure that local workers at the port have the fastest possible access to the inventory data they need to keep cargo moving. Distributed SQL represents a significant evolutionary step in cloud-era database architecture, addressing many but not all trade-offs inherent in distributed systems. It successfully bridges the gap between the reliability of the past and the scale of the future. For organizations looking to modernize their data stack, the following general recommendations apply. First, prioritize consistency over complexity. For any application involving systems of record, money, identity, or inventory, do not compromise on strong consistency. The operational cost of fixing data anomalies in an eventually consistent system far outweighs the initial investment in distributed SQL. Second, design for distribution early. To truly harness the power of scale and locality, developers should design their schemas with distribution in mind. This includes choosing primary keys that avoid hotspots and understanding how data will be partitioned across regions. Third, evaluate for multi-cloud resilience. One of the greatest strengths of this technology is cloud agnosticism. Organizations should look for solutions that can span multiple cloud providers, for example, Amazon Web Services, Microsoft Azure, and Google Cloud, to avoid vendor lock-in and provide an additional layer of resilience against provider-wide outages, albeit with increased operational complexity and cross-cloud latency considerations. This table is a summary. You can pause the video to read it. Resume the video when you are ready for the conclusion. In conclusion, as we move toward an agentic scale of computing, where AI agents and billions of IoT devices interact with data in real time, the underlying database must be as resilient and flexible as the network itself. Distributed SQL provides that foundation, ensuring that data is always where it needs to be, always accurate, and always available. Thank you for watching. So what do you think about distributed SQL? Please drop your comments here. If you found this presentation informative, please share, like, and subscribe. Goodbye.